So it's time to define immunity. The immune response is a complex series of reactions of the body involving white blood cells to a non-self antigen. An antigen is a compound, a toxin or other foreign substance, for example, that is recognized by the immune system of the body, especially through the production of complementary antibodies. Non-self is a material that is foreign to the body of an organism. Self is material that comprises the organism in question. The Cambridge definition of immunity is a little bit odd, and it bears reading from their textbook directly, because the way they state it, it has some merits, but otherwise it's odd. But a person who experiences few or no symptoms after exposure to a pathogen is said to have immunity. That part's fine. In the event that a person becomes a carrier of a disease and could still pass it on to others, so long as they don't show symptoms, Cambridge still calls them immune. In certain cases, this may be true. You can't get chickenpox again after you get chickenpox, but you can have a reemergence of chickenpox as shingles. So you can still be a carrier of chickenpox, but you're immune to a new infection. That's the only way I can sort of parse their definition and say that it's sort of accurate. But the carrier status of an individual doesn't work, because tuberculosis, if you don't show symptoms, you're latent tuberculosis. That doesn't mean you're immune. Cholera, you're not immune to cholera if you're not showing symptoms. 75% of people don't show symptoms with cholera. That's just mostly normal. HIV, you're not immune to HIV if you're not showing symptoms. You might be in the latent phase. You might be in dormancy phase. That's their definition doesn't quite fit. But yeah, it's very strange. But they are the ones testing you. This first part is definitely accurate, though. If they experience few or no symptoms after exposure to a pathogen, they're said to be immune. But how long after exposure depends on the disease. Depends on which pathogen, depends on which infection. All right. So, another shameless plug. Crash Course. Crash Course, the channel, another of my favorite channels. Go watch them. They're very good. Not being paid, just a fan. Right. Immune system. There are 3 lines of defense to the immune system. You have your innate immunity, your non-specific defense mechanisms. And that is split into 2 lines, your first line and your second line. The first line is a simple barrier protection. This may seem like a crazy concept, but if the pathogen can't get into you, it can't make you sick. So your skin, your mucous membranes, the secretions thereof, keep you from getting sick. Stomach acid prevents you from getting sick with cholera if it kills all of the cholera. If it kills all of the Vibrio cholerae bacteria, I should say. The secretions of the skin. Oil, sweat, sebaceous oils, sweat, and other compounds that I'm forgetting off the top of my head. They are creating a caustic chemical environment that prevents the growth of many different types of bacterium and fungus. However, you also have a lot of bacterium and fungus already living on your skin, which also actually prevents the growth of other bacterium and fungus because they don't like competition either. That's called normal flora. Secretions of the mucous membranes. your lung tissues, the mucus, the seromucus glands and the goblet cells secreting mucus. Those count. Your second line of defense are non-specific defense mechanisms. Macrophages and other phagocytes like neutrophils, they are part of the non-specific immunity, and also the inflammatory response, which we will discuss. That is part of the non-specific defense. That is the innate immunity, the non-specific defense. This is how you will respond to everything, regardless of what it is. Everything will be responded to by these systems in the same way. Everything gets treated the same way by these two lines of defense. The adaptive immunity is your specific defense mechanisms. With the innate immunity, it was right away to a brief span of time, a few hours. The adaptive immunity takes time. It takes days, many days. This is your third line of defense. It's mediated by lymphocytes, B cells and T cells, B lymphocytes and T lymphocytes. And it is antigen-specific immunity. And it is mediated by antibodies, and you can produce memory from your adaptive specific immune response. White blood cells, if you recall from Unit 4, when we discussed the different types of white cells, they all originate from the bone marrow, from hematopoietic stem cells. We are going to discuss phagocytes and lymphocytes now. We can separate them by a number of categories. You can separate them by progenitor cell, myeloid and lymphoid progenitor, which is important when we discuss leukemias. You can separate them by visual appearance, which is important when we discuss granulocytes and agranulocytes, which is how we identify them. It is important, and phagocytes and lymphocytes is how we're going to describe them now when we discuss innate or non-specific immunity, and lymphocytes when we discuss specific antibody-mediated, cell-mediated immunity. We've already discussed the stem cell origin. Our phagocytes are the monocytes, which mature in the tissues into macrophages and neutrophils. I'm sorry, into macrophages. And also neutrophils are phagocytes. These can respond to isolated pathogens alone, or they can use the assistance of antibodies that have been produced by the lymphocytes in order to assist them in binding the antigens and allowing them to more easily phagocytize the pathogen. So these are those cells again. This is a neutrophil. This is an eosinophil and a basophil. These are the lymphocytes, the various lymphocytes. And this is a red blood cell. And this is a monocyte. Monocytes are the largest. And monocytes, when they exit the tissues, they become macrophages. Sometimes they will become endothelial macrophages and remain on the endothelium. When they enter the tissues, they become resident macrophages, and it depends where they go, what tissue they go into, that determines what they become. If they go into the central nervous system, they can become microglial cells, which do not have the same function. They can become osteoclasts in the bone, which do not have the same immune function. They can become Kupffer cells in the liver. They do have the immune function. They can become Langerhans cells in the skin. They do have the immune function. They can become dendritic cells in the tissues. They do have an immune function. And those dendritic cells and those macrophages, they can return to the blood or go to the lymph nodes in order to present their antigens that they have processed to lymphocytes for the purposes of improving antigen-specific immunity response. So that brings us to discussing antigen-presenting cells. Antigen-presenting cells are a heterogeneous group of immune cells that mediate the cellular immune response by processing and presenting antigens for recognition by certain lymphocytes, such as T cells. Classical antigen-presenting cells include dendritic cells and macrophages, which are both mature monocytes, and B cells. B cells are also antigen-presenting cells. Those are lymphocytes. They present antigens to T cells as well. Neutrophils, although they are phagocytes, are not antigen-presenting cells. The reason for this is because as soon as they start engulfing things, they're going to explode. They explode as part of their means by which they assist in increasing the immune response, the inflammatory immune response, and also killing lots of bacteria. In fact, pus is composed primarily of the carcasses of dead neutrophils, along with everything they've killed. And they kill a lot of stuff. And they are produced in large numbers. So now let's talk about the Fc receptor. The Fc receptor, drawn as a little goalpost on the cell when you draw it rough, is a protein that's found on the surface membrane of certain cells. It includes B lymphocytes, follicular dendritic cells, natural killer cells, macrophages, neutrophils, and others. They are part of the immune system function. They assist in allowing antibodies, which we will discuss in greater detail later, to bind. The Fc region of an antibody will bind to the Fc receptor. And when that happens, it allows for easier access of that phagocyte to engulf the pathogen. So antibodies are binding to antigens on the surface of the pathogen, and antibody Fc regions are binding to the Fc receptors, which are attached to the surface of the effector cells. It's a thing that is attached to it's a thing with stuff attached to it that has a thing attached to it that attaches to a thing that's attached to a thing. There's a lot of attachment going on. There's a lot of attached stuff. It's like Voltron. The more you hook up, the better it gets. So this is Fc receptor mediated phagocytosis. Fc receptor mediated endocytosis, known as phagocytosis. Fc receptor mediated phagocytosis. So the antibody binds to the bacteria. In this case, it's a bacteria. Could have been a virus. Who cares? It's binding to antigens on the surface of that pathogen. In this instance, this is a bacterium and this is a macrophage. Could have been something else. Doesn't matter. The antibodies bind to the antigen. The antibodies bind to the Fc receptor on the cell surface of the effector cell, our macrophage, this time. And that stimulates via cell signaling way back from Unit 2. Unit 2. Way back from Unit 2, via cell signaling, stimulus, signal transduction, cellular response. The stimulus is the antibody connecting to the Fc receptor. The signal transduction is the activating signals from the Fc receptor all the way through on the opposite side of the membrane. It's connected to other things down there. That stimulates the cellular response of the membrane producing, the macrophage producing cytoplasmic projections that surround and engulf this pathogen, the bacterium. in this case. Once the bacterium has completely engulfed the pathogen, those membranes fuse. Those cytoplasmic projections fuse into a membrane-bound vesicle called the phagosome. The phagosome, you're not done yet. This is not yet done with phagocytosis. Now, lysosomes come along, and they fuse with the phagosome, forming a phagolysosome. You just add the prefixes together. And those lysosomes contain lytic enzymes and acidic and harsh chemical conditions in order to break down that pathogen into its constituent parts. Digestion, chemical and enzymatic digestion. Antigen processing will occur at this point. The antigens that the macrophage wants from this dead bacterium will be taken out and presented on the surface of this macrophage. As an antigen-presenting cell, that's its job. It can use some of this stuff as food. The rest, it will have to exocytose. Exocytosis is where this phagolysosome vesicle will fuse with the plasma membrane of the cell itself, and the vesicle membrane and the cell membrane will become one membrane, and the contents inside the vesicle will be pushed out of the cell. The inside of the vesicle will become the outside of the cell. The inner membrane, the inner surface of the vesicle will become the outer membrane surface. And the outer membrane of the vesicle will become the inner membrane surface of the cell. So this is inflammation. The 5 pillars of inflammation: heat, redness, swelling, pain, and loss of function. I forget the Latin for loss of function, but it's calor, rubor, tumor, and dolor. I honestly forget loss of function in Latin. My apologies. I probably should have looked it up. But here's actually a closer look. Yes, inflammation hurts. It's unfortunate that you have to experience something that sucks for you. But each of those things is doing something for you. Healthy skin, for example, is not inflamed. You have intact skin, you have infector cell in the interstitial fluid, you have a blood vessel with white blood cells inside and a red blood cell here for effect, for comparison. Then you scrape your knee. There is now dirt in the wound. A blood clot will begin to form to maintain that barrier protection, to maintain the first line of defense, to maintain barrier protection. Dirt and grit and bacteria will ride along with that dirt and grit into your interstitial tissues, your connective tissue. Your effector cell will engulf these bacteria, and in the process of engulfing these bacteria, it will release cytokines. These cytokines are chemical messengers. There are many different chemical messengers. There are many different cytokines. Many different cytokines. One of which, tumor necrosis factor alpha, TNF alpha, is a pro-inflammatory cytokine. And that one we'll discuss very briefly later in reference to one thing. Now, these cytokines have many jobs. One cytokine will cause dilation of that blood vessel. When a blood vessel vasodilates, vessel, dilate, increase diameter, the blood flow increases. If blood flow increases, the pressure between the inside and the outside is different. This allows for diffusion to increase from inside the vessel to the outside. One of those cytokines may increase the endothelial pore size. And if there are pores in the endothelial membrane, in the endothelial wall rather, then protein and fluid can leak through. Those proteins and fluids are allowing the clot to form and strengthen. The blood clot that is strengthening that barrier protection and sealing up the wound, preventing further bacteria from entering your tissues. So your swelling is a result of the expansion of the vasodilation and the dilation of the pores of the blood vessels, allowing proteins and fluids to enter that allow for that clot to form to maintain barrier protection. So yes, swelling is helping you. Redness occurs as a result of the expansion, the vasodilation of the blood vessel. Because a dilated blood vessel has more blood flowing through it. More blood has more red cells. More red cells means more oxygen to the area. That's good. But it also means it's redder. The increase in pore size also allows for white blood cells to exit through chemotaxis. Now, chemotaxis is spelled CHEMOTAXIS. CHEMOTAXIS. Essentially, they are being drawn toward chemicals. Taxi, like the taxiing of a plane. Chemo, chemical. They are being drawn by chemicals. And those chemicals they're being drawn by? Cytokines. Pro-inflammatory cytokines. They're going to assist in removing the bacteria that have entered that interstitial space, thereby producing more cytokines. So, one of those cytokines will also increase the temperature by signaling the central nervous system to increase the body temperature in the area. It will also increase the metabolic rate of nearby cells. So they start producing a lot of heat. Because higher temperatures increases the rate of reaction of chemical processes in nearby cells, which allows for the immune cells to do their jobs better of killing bacteria. So heat is part of the healing process. So we've covered heat, swelling, redness. Now let's talk pain. Pain is keeping you from touching it. It's also increasing blood flow to the area. That's actually a central nervous system stimulating factor. Pain increases blood flow to an area. It also is a byproduct of the nerves in the area being caught in this chemical warfare. Loss of function. If it's swollen, you can't move it as well. If it's hot and painful, you don't want to touch it. You're not messing with it. You're letting your immune system do its job. So we begin with nonspecific and specific interactions of the immune system. So we've discussed what comprises the nonspecific immune system. Those are B cells and T cells. As a general rule, the B cells are going to focus on antigens and pathogens that are outside the cells, invaders outside the cells, and T cells are going to focus on invaders that are inside the cells. So, with that being the focus, it's important to understand exactly how these systems interact. But it's also important not to forget that there is an interaction between the non-specific and the specific immune system. And this chart really does sum it up. So you have a first exposure to an antigen. And that first exposure, that first antigen, will be engulfed by an antigen-presenting cell, which could be which is not a neutrophil, which could be a macrophage, or in some cases it could be a B cell. But if the macrophage is engulfing it, that is the non-specific cellular-mediated response. That is the second line. That is the second line of defense. So if the antigen-presenting cell engulfs that antigen, then it will stimulate helper T cells and cytotoxic T cells to proliferate. It will stimulate them to proliferate, and it will also stimulate them to produce their functions. The helper T cell's function is to release cytokines, as we discussed. The helper T cell's function is to release cytokines, and those cytokines will stimulate B cells, and those cytokines will also stimulate other cytotoxic T cells. Those cytokines will also stimulate themselves, the helper T cells themselves. The first antigen, by the way, will also be stimulating B cells directly. Now, once these helper Ts, cytotoxic Ts, and B cells get stimulated, they will give rise to more of themselves and memory cells of themselves. So each of these cell types has its own memory cell. A B cell, which is the antibody-mediated immune response, the humoral immunity, will divide and differentiate, divide by mitosis, clonal expansion, into, and then differentiate into plasma cells and memory B cells. In order to differentiate into memory B cells, it needs to be stimulated by cytokines from helper T cells. For that extra step to occur, it needs stimulation from T cells, from helper Ts. But it will divide and differentiate before that into more of itself and plasma cells, just not its memory cells and the specific plasma cells. Now, helper Ts will give rise to more of themselves. They'll loop around, make more helper Ts once they are stimulated, thus increasing that cytokine activity. And they will also give rise to to memory helper T cells. More helper Ts floating around can stimulate more stuff, and the memory helper Ts will have those T cell receptors present in order to specifically bind to those antigens presented. Now, the stimulated cytotoxic T cells, the natural killer cell, or the killer T cells, whatever you want to call them, but stick to one thing. Only call them one thing. Choose which one you want to call them, and call them that. Consistency is key. Cytotoxic T cells will divide by mitosis and cytokinesis and differentiate into memory cytotoxic T cells and active cytotoxic T cells. Those cytotoxic T cells will directly lyse infected cells. They will directly kill cells that have been infected by pathogens. The memory cytotoxic T cells will carry on that T cell receptor. Now, let's say there's a second exposure to the antigen. If there's a second exposure to the antigen, it will stimulate all of these memory cells. Memory B cells will be stimulated. Memory T helper cells will be stimulated. Memory cytotoxic T cells will be stimulated. That stimulation will allow them to divide and differentiate into more of their effector cells. and more of themselves, more of those memory cells again. And that will indicate our secondary immune response, which will be stronger and faster than the previous one. So memory B cells, when they get stimulated, will produce plasma cells and more memory B cells. Plasma cells, by the way, produce antibodies. They produce antibodies that float freely through the plasma. And antibodies plus plasma is serum. Remember that from Unit 4. And antibodies have a number of functions that we will discuss later. These memory helper T cells, when they divide and differentiate into helper T cells and more memory helper Ts, they're going to do the same job as the helper T cells originally did. They're going to continue stimulating memory helper B cells, and they're going to continue stimulating cytotoxic T cells to do more of that job. So this is primary antigen exposure, secondary antigen exposure. Primary challenge, primary antigen challenge, secondary antigen challenge. Primary response, secondary response. Slow and low, fast and quick. Because you were prepared. Memory cells are what make memory. Memory cells are what make immune memory. And it is memory B cells, memory T cells of the helper and cytotoxic variety. That is what makes immune memory. So if you're asked what the similarities between B cells and T cells are, in both cases, you will have a highly variable protein receptor that is unique to the individual naive lymphocyte. In both cases, you will have activation by an antigen recognition. In both cases, you will have clonal expansion and differentiation into effector and memory cells. In both cases, their products will elicit further immune response. The differences. These are the receptors on the T cell and B cell. On the B cell, it is a membrane-bound immune globulin. This membrane-bound immune globulin is a class D immune globulin, IgD, on the B cell. And it is shaped with 2 heavy chains and 2 light chains with a variable recognition sequence, the B cell receptor region. This region here is for cell signaling. And you remember cell signaling from Unit 2. When an antigen attaches, an antigen that is specific for the region here, an antigen that is specific for the antibody receptor here, binds, that stimulates, that acts as a stimulus. That acts as a stimulus, which promotes signal transduction, the second step, and then you'll get a cellular response. That is activation of the B cell to produce clonal expansion and then differentiation. So this is cell signaling, and this is the receptor for it. This is the receptor, and this is where signal transduction will arise from. In the T cell receptor, it's the same idea, but a different setup. You have one recognition site that is specific for an antigen. This is a T cell receptor, TCR for short, and it is specific for an antigen. This region down here is what sends the message to the cell, the signal transduction area. This is for cell signaling. So one site in T cells, one antigen-specific binding site on the T cells, 2 antigen-specific binding sites per antibody receptor on the B cells. Now, this image is actually not as good as the one straight from the Cambridge textbook, which I took a very bad picture of. And let's see if it shows up on camera. It's not bad. All right, we'll continue. So this is the B cell system. It's not terrible. So for B cells, as we know for all white blood cells, they arise from hematopoietic stem cells. These are of lymphoid origin, lymphoid progenitors, in the bone marrow. They divide in the bone marrow by mitosis. While still in the bone marrow, they will reach maturity. And as part of reaching maturity, they will produce their antibody receptors. They will produce their antibody receptors. Each B cell will have its distinct antibody receptor that is specific for one antigen. There is antigen specificity of antibodies. Antibody receptors have antigen specificity. That is a key point-earning phrase. So, all the mature B cells that arise from the bone marrow will have different antibody receptors. When you have an antigen stimulate, when an antigen is exposed, when you are challenged by an antigen, only one of these B cells will have the proper antibody binding site for that antigen. This middle one right here just so happened to have the right antibody binding site for that right antigen. Why did it have that one? It was lucky. It was random. It didn't plan for it, it just happened to have it. We'll explain that in a moment. Now, that is recognition, and that activates or sensitizes the B cell, which initiates clonal expansion, which is mitosis and cell and cytokinesis, which clonal expansion, and then differentiation, where the different daughter cells take on different traits. And some of those daughter cells will become memory cells. Differentiation probably should have gone down here. Some of those will become memory cells, and some of those will become plasma cells. Now note this. Memory cells cannot form without stimulation by T helper cells. B cells must present antigens to T helper cells in order to receive the proper signals to complete their final maturation into memory and the highly specific, high affinity, IgG producing plasma cells. That will get you the highest, that will get you additional points when discussing the maturation of B cell mediated immunity. Now, if you are presented with that antigen again, it will bind to the receptor of these now more numerous B cells than the first time. The first time there was just one floating around because it was lucky. This time there's a whole clone army of memory B cells. And that clone army is more likely to come across antigens, and when multiples of them come across it, they don't need T cell activation now. They can just directly differentiate into more of their own type of memory B cell, and more plasma cells, which produce more antibodies specific to that antigen. So this is B cell mediated immunity. This is humoral immunity. Antibody secretion. The secretion of specific antibodies for a antigen. This is mediated by B cells. B stands for bone marrow because they mature in the bone marrow. It is important for you to understand this. B cells can come across their antigen that activates them by either being presented it, finding it on their own, by either being presented it by antigen-presenting cells like macrophages, or finding it on their own in the blood system, in the blood circulation. In order to achieve their final stage of high affinity IgG producing plasma cells, they need to be activated by helper T cell stimulation. Otherwise, they will only produce low affinity IgM, and they will produce no memory B cells. They will only produce more of themselves, but not memory B cells, long-lived memory B cells. So, B cells can be antigen-presenting cells too. They can find and bind to their antigen, engulf it, process that antigen, and present it via an MHC class 2 antigen-presenting complex, major histocompatibility complex class 2 surface protein, to helper T cells, which will then release cytokines to activate them. And this is what I've been saying the whole time, that with that activation, they will produce high affinity IgG and memory B cells. Without that activation, they can produce class switching plasma cells and low affinity IgM, but not in sufficient quantities. Now, the antibodies they produce perform a number of functions. Antibodies can function in neutralization, which is they inactivate the microbe, virus, or toxin. They prevent it from performing its action. So a virus that is covered in antibodies cannot enter a cell, and therefore cannot proliferate and kill that cell. A toxin that is covered in antibodies cannot, if it is a competitive inhibitor, for example, compete with the active site of the enzyme it inhibits. If it is a allosteric inhibitor or an allosteric effector, its shape is changed by those bound antibodies, and it can't do its job either. Or it is no longer able to cross membranes and affect enzymes inside cells because the IgG is quite large. Large molecules like antibodies do not easily cross membranes. So binding antigens with antibodies makes them unable to perform their functions. That is neutralization. Opsonization is a way of tagging these antigens. You tag the antigens that are either bound to a pathogen or freely floating large pieces of something, and it makes them easier for macrophages and neutrophils, and other phagocyte type immune cells to dock the Fc region of the antibody to the Fc receptor and therefore begin phagocytosis. Fc receptor mediated phagocytosis, which we discussed in the last video. Yes, in the last video. So, NK cells, natural killer cells, or cytotoxic T cells, for your purposes, they also have Fc receptors that allow them to dock with antibody-bound pathogens and get a good close-up on them so that they can deliver their toxins to destroy the membranes, to destroy cells directly, to initiate apoptosis or to initiate cell death of some way, by some means, some chemical means. Another way Another way in which antibodies can function is through the activation of the complement system, which is not directly tested by Cambridge. However, it may or may not be worth additional points. So just say complement activation, which leads to direct lysis of microbes, activating the complement system. Any more information than that is not part of the Cambridge lesson planning, and therefore is not likely to be tested by Cambridge directly. But if you're asked a question about the functions of antibodies, it is a function of antibodies. Therefore, you should be able to get points for it because it is correct information. They are also, complement activation is pro-inflammatory, it also assists in opsonization, and it directly lyses microbes. So complement activation, opsonization, and neutralization. Those are the three functions of antibodies. Those are the three functions of antibodies. Now let's talk about cellular immunity, cell-mediated immunity, the T cells. We'll talk about T helper cells, and then we'll talk about T killer cells or cytotoxic T cells. Helper T cells or T helper cells, their activation produces a clone of cells that release cytokines, which stimulate and strengthen both the humoral and macrophage responses. They stimulate everything by producing cytokines. Cytotoxic T cells, their activation produces a clone of cells that can directly kill infected cells. Both types produce memory cells, as we discussed before. So this is directly from the Cambridge textbook too. Let's make sure that it shows up on the video. It's not readable, but it's visible, and I'll explain it in words. So much like the B cell images before it, they arise in the bone marrow because all white blood cells begin in bone marrow. All white blood cells and red cells too. All blood cells begin as hematopoietic stem cells. These also arise from lymphoid progenitor cells. And they divide by mitosis and cytokinesis. But instead of maturing in the bone marrow as well, like the B cell, B stands for bone marrow, the T cell exits the bone marrow and migrates to the thymus gland, T-H-Y-M-U-S. 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 The thymus gland is located in your chest, above your heart, and it disappears around the age of 4 or 5 or so. If you have a persistent thymus gland, you have other problems, or it's associated with other problems that we'll talk about soon as well. Each of those T cells maturing in the thymus will do the same sort of thing as the B cells did. They will produce surface membrane bound receptors, each one for a unique antigen. Antigen specific T cell surface receptors, TCRs, T cell receptors. So they mature in the thymus. That's what the T stands for, thymus. Mature T cells, once they are released from the thymus, know their job. They are already helpers or killers, or 3 other things that you don't learn about. 2 other things that you don't learn about in Cambridge. They already know their job. They are already there. The only differentiation they will do is after they have been presented antigens. And this image is a little blurrier on the screen too. After they've been presented antigens by an antigen-presenting cell, an infected body cell, both of them will divide and differentiate into more of their effector cell type, divide into their effector cell types and memory cells of their cell types. Both of them. Helper Ts will divide into effector helper Ts and memory helper Ts. Killer Ts will divide into memory killer Ts and effector helper Ts. The helper Ts will perform their function by releasing cytokines, secreting cytokines that stimulate B cells to divide and form plasma cells and memory cells. They will also stimulate various other immune response, various other factors of the immune response, including pro-inflammatory responses, including more phagocytic response, all those things. The cytotoxic T will seek out and find infected body cells, bind to their presenting surface antigen, and then get very close, almost touching the membrane, and then release a series of vacuoles containing a toxin that places a large pore in the cell membrane of the cell that they are approaching and binding with the surface receptor of. The pore in the membrane is an opening that allows water to flow freely, uninhibited. Instead of the semi-permeable plasma membrane that already existed, it is now a freely permeable pore. And the inside of this cell, this infected cell, has a higher salt concentration, a lower water potential than the outside of the cell. And water will follow. It will flow down its concentration, down its water potential gradient. We are using water potential as the terminology that we need to use. It will flow down its water potential gradient by osmosis from the outside cell environment, or the extracellular environment preferably, to the intracellular environment, or from the outside of the cell into the cell. You must specify from where to where. Down its concentration gradient, down its water potential gradient. I keep making that mistake. Down its water potential gradient by osmosis, from the outside to the inside. And when that cell swells, it has a plasma membrane, not a cell wall and a plasma membrane. There is no protection offered against rupture, and it will rupture. It will rupture and burst and deflate and So these slides just show specifically separating out the T helper cell differentiation from the other one. It's not nearly as involved as the previous Cambridge textbook one. And this is just separating out the cytotoxic T cell differentiation. It's also not nearly as involved, but it's brighter. So this is a walkthrough of the logic behind how memory formation occurs from a molecular standpoint, from a genetic standpoint. So antigen specificity. How does antigen specificity occur? Antigens, we know, bind to a protein structure that is specific for them. That protein structure could be a T cell receptor or it could be an antibody. Doesn't matter which one we're talking about. So that specificity of that protein, the specificity of any protein, whether it's an enzyme or receptor or a membrane transport protein or some kind of carrier molecule, doesn't matter. The specificity of any protein is always reliant on three-dimensional structure. Three-dimensional structure The 3D structure you can trace back from quaternary structure if it has multiple chains, or tertiary structure if it only has one chain. Down the levels, secondary and then primary. Primary is the individual amino acids that make up that structure's sequence, the sequence of amino acids. And that primary structure is a translation of mRNA, which after post-translational modification, or rather after post-transcriptional modification, excuse me, comes from DNA. So DNA determines, after several steps, the specificity of antigen, the specificity of receptors, these proteins, antibody or T-cell receptor, to antigens. It all comes down to DNA. The genetic code is determining antigen specificity. Now, proteins can be anything, any sequence, and they can come from anywhere. And microbes, and pathogens thereof rather, have many generations to R1. Humans live for a relative long time, and a very long time when compared to, say, 20 minutes of E. coli. So E. coli is dividing every 20 minutes, and we are, well, not dividing, but living for 70, 76, 80, 86, whatever, however many years. If you are going to live that long, you are going to experience many generations of bacteria. Each one could have a new mutation at any given time. And that mutation can result in a brand new antigen that has never been seen before on the face of the earth, that has never existed before in all of history, which means none of our ancestors would ever have come across this antigen. There is no way that our DNA can come pre-coded for every possible outcome. For every possible outcome of every possible change, every possible mutation, of every possible bacteria, of every possible genus, of every possible species, ever, under the face of the sun, on the face of the earth, and below it, and above it, everywhere. Because bacteria can fly. They can be carried on the air. They can be buried under the dirt. They can live in the sea. Bacteria is everywhere. And viruses are everywhere. And fungus is everywhere. Everything we can come across can have unique sets of antigens and can mutate in order to change. And those changes we may never have experienced before. So we need to be able to change our DNA in order to meet the antigen specificity requirements of our antibodies and T-cell receptors for those antigens, those new antigens that never existed before on the face of the earth. We need to be able to respond to them if we're going to live that long. So that means that we need to be able to mutate in our own lifetime. Each cell needs to have a highly variable region of DNA that can mutate and change the way it is encoded. It can either be mutated or it can have a large series of introns and exons that can be interchanged differently, however that works out. As long as there is a highly variable region, mutations could be one way, exons and introns could be another. The combination of both is the most likely. That produces many different protein structures that can be different recognition sequences. If we produce an antibody or a T-cell receptor that binds to no antigen, that's fine. If we bind to something that doesn't exist yet, that's fine. If we bind to if we create something that, or rather, if we produce something that doesn't exist. We produce something that binds to a thing that we've never experienced before. That's the idea. If we produce something that we've experienced before, it won't get used again. It doesn't. It's unnecessary. It won't be used because we've already built something like that. When a protein's variable chain, when the T cell receptor or B cell receptor has a complementary match to an antigen, that allows that cell to activate. And that cell will create, that cell will proliferate by mitosis and clonal expansion. And that means that it and its variability and and its specific outcome of that variability will be conserved and replicated. So if you don't bind to a chain that you created, it will just go away when that cell dies and no harm done. You didn't need it, it didn't get used, done. If it was needed and it got used, you make more of it. So you are selecting for the things that are necessary, and the things that are not necessary and do not get used get weeded out over time by senescence. So memory cells of both the B and T cell varieties are cloned from cells that had the correct genetic sequence, that made the right, that had the right series of fortunate events to create a receptor that could bind to a specific antigen. And so all of their genetically identical daughter cells will have that very same T cell receptor or antibody. And that same protein sequence will be conserved. That's where you get antigen specificity from, through memory. It's a series of mutations that get conserved. A series of mutations or a series of conserved modifications. So this is the primary and secondary response curves. These are serum antibody titers, and we say serum antibody titers because plasma and antibodies equals serum. Blood without cells and without antibodies is plasma. If you take the serum out of blood, you just have cells. Remember your components of blood from Unit 4. So you begin with no serum antibody levels. You have no antibody titers. The titer is just the level. How much circulating antibodies you have. Then you have an exposure. You have a primary challenge. You have a challenge by antigen X. You are challenged by antigen X. You will have a lag time where no response will occur. This lag time can be a variable length. It could be a day, it could be a week, it could be 2 weeks, depends. Because antigen X has a specific 3D conformation, and the anti-X B cell is the one that has the surface membrane bound antibody that is specific for antigen X, by luck, a series of conserved mutations and modifications. The B cell that is anti-X will proliferate and produce antibodies by differentiating into plasma cells and then memory B cells. So your antibody titers will rise, peak, and then fall. Once the antigen has been cleared, you start to see a fall in antibody levels. As you use them up and the necessity for having plasma cells decreases. As you have fewer exposures from the antigen to the B cells, you differentiate fewer plasma cells. As the plasma cells die off, the circulating levels of antibodies also declines until you are left with a higher titer of antibodies than the zero you started with. So now you have a level of circulating antibodies than before. Where before you had 0, now you have some. Here you have a challenge by antigen X and antigen Y. You have never seen antigen Y before. So the response curve will look exactly like the primary response to X, because this is a primary response to Y. And antigens are specific to, or antibodies are specific to antigens. Because antibodies are specific to antigens, the primary response to Y will be exactly like the primary response to X. This is the first time you're seeing Y. So it follows the exact same curve. And you have the circulating antibody levels. As your plasma cells decline, you'll have memory cells form, and you'll have a higher antibody titer than you started with, higher than 0. The secondary response will be faster and higher than before. You will have more plasma cells than before because you have more memory B cells floating around. You have more memory B cells floating around than you had naive B cells the first time. So more plasma cells will differentiate, more antibodies will be produced faster because you don't need T cell activation this time either. So a faster response and more antibodies circulating than you ever had before. And when the peak settles down, when you return, you will have a higher level of circulating antibodies than you ever had before. And this is the idea behind boosters on vaccines too. You hit them once, and then you hit them again, and then you hit them again, until the circulating levels of antibodies are high enough to produce sufficient levels for immunity, for sustained immunity. And this is why you have to get a booster shot every 10 years for tetanus, unless you get a dirty wound, in which case it's 5, or 3 if it's a really dirty wound. And that's the reason why. It's because your amount of circulating antibodies tapers off after a while, and you need to have that secondary response again. So some common mistakes. Phrases such as remembers the disease and fights the disease are unacceptable. You must use scientific terminology. The immune response, memory B cell clone formation, memory T cell clone formation, helper T cell, memory helper T cell clone formation, T cell activation of B cells to clonally expand and differentiate into plasma cells and memory B cells, producing an immune response and memory in the event of future antigen exposure. In the event of future antigen exposure, the memory B cells will activate again through binding of their surface antibodies to the antigen to divide and differentiate and clonally expand, to divide and differentiate into more plasma cells and more memory B cells once again, without the assistance of T helper cell activation. That phrase, that whole big sentence right there, full credit. We'll stop the video there.